Good afternoon, Mr. Schweitzer, and we're going to look at an application of kinematics that involves relative motion on a linear line between more than one object. So the question says here, all right, grab a pen quick. We have two objects on a line, and we call this like person A and this person B. So I'm just going to kind of highlight the problem, give you an idea of what it looks like. Looks like my pen's slowing down. Okay, so that being said, all right, so what do we have here? Well, what variables do we have? Well, we have the variables that are typically in the distance formula, which is the location of the person, xt, and then we have the current location, and of course this line is x, so they share the same x line, so they share the same. So what variables do they share? All right, they share, like they're on the same x coordinate plane. X initial, sometimes xt is also referred to as s, and Mr. B will call it the S formula, plus velocity initial times time. Okay, they are actually in the same time frame, like their times are the same. That's what one they share. And then 1/2 at squared. Okay, so this would be all of A's variables, and these are all of B's variables as well. Xt equals xi plus bit plus 1/2 at squared. Okay, one more thing that they share was the frame of reference. Frame of reference. So what does that mean here? Well, okay, well, it's saying the same frame of reference, meaning that, okay, there's some relative mark that would be like 0. Okay, and then we can set that 0 to wherever we want. In fact, typically speaking, we wouldn't put it in the middle. We could, but typically speaking, we might say, okay, I want to set A at 0. Okay, and then maybe B is like plus 100 or wherever B is located. We need to have some information here. So we've already, by doing this, I've designated that this way is my positive and that this way is my negative. So the way these problems typically work out is we're looking for a couple of different things. One, if they're chasing each other, okay, they can both be moving towards each other. So they both can have their own velocities, and they both can have their own accelerations. It's just a plug and chug problem at this point, where B can be moving towards A can be towards B could be moving away from A, and B could be moving towards A. Now we typically want to know when A catches B. Well, if B is farther away and traveling faster, well then we're never going to catch. So typically speaking, in a problem, there's going to be some point where A catches B. So we're typically looking for this time. Okay. Now there's a time variable here. There's a time variable here. Okay, and there's a get that guy out of there. And there's a time variable here, there's a time variable here, there's a time variable here. There's all the same times. So the way we solve for that time could be as simple as just solving for this t, or if we need to use a quadratic because we have a square and a component here, then we got to use a quadratic. So typically questions are going to be one of two things, looking for time, okay, that they connect. Time when they are at the same xt. Okay, so they want to know, and then they likely want to know where is xt. That is the problem. Okay, these are pretty simple problems mathematically. What we're doing here is essentially we want to know when these two things cross the same spot. So all we do is set these two equations equal to each other, and it's going to be xi plus vit plus 1/2 at squared equals xt. Of course, that's going to be the same xt as here, equals xi plus vit plus 1/2 at squared. Now, the general theory here is that we're going to cross off this x, because set this equation equal to this one, and we'll solve for t. And then t, you can plug t into either of these two formulas, and you can solve at that point. You have everything you need to solve for xt. And of course, if you put the t in this formula, or you put the t in this formula, you get the same xt, because they're in the same spot at that time. So you can choose which one you want to be. Okay. Not everything needs to have an initial velocity. Not everything needs to have an acceleration. So if A and B could easily start out with no velocity, okay, they could have a velocity and an acceleration, or no accelerations. Okay. Sometimes if you're missing the accelerations, it makes the problem easier, which what the next problem looks like. Let's just show you how this kind of sets up. A motorcycle is traveling 130 miles per hour, which is 63 meters per second down a highway. This car sees the motorcycle and tries to catch her. After the motorcycle has traveled 3,000 meters, the cop is now traveling 100 miles per hour or 67 meters per second. So they're catching each other. So let's set a little picture here. Essentially, we have this cop. Sorry, not the best picture here. And they're traveling down the way here, and the motorcycle is located down the ways a little farther. Okay. Now, this is saying he's 3,000 meters. So I like to, whenever I'm running these problems, either list the variables out that I have, or sometimes I like to just write the formula out. So xi plus vit plus 1/2 at squared equals xi plus vit plus 1/2 at squared. Okay, and you can start plugging in the values that you have here. So in this situation, the velocity initial, okay, this is all for the cop, this is for the biker. So the cop, you start plugging in. At this point, it's just a math problem, nothing more than that. And so we're going to move pretty quickly at this. The motor's traveling 140, so 63. So initially traveling 63, and t. xi is actually 3,000. Now notice that this guy is positive because he's traveling to the right. If he was traveling towards the cop, then he would have a negative ti. Okay. No acceleration, so this whole factor is 0. Equals, now this guy is at low, I'm going to set this frame of reference at 0. So it's at 0 plus vi, which is 67, t equals that. And this is, again, 0 because there's no acceleration. At least it wasn't listed. Okay, so at this point, what you do is just solve. Because I don't have a square component, I don't need an quadratic formula. So in this situation, I'm going to just get all my t's to one side. So minus 63t gives me 4t equals 3,000. All right, and then divide the 4 out, and I get my t equals 3,000 divided by 4 is 750, and my unit I'm using consistently through here is seconds. All right. Now that is the answer for how much time will it take to catch this guy. Okay. All right. So what else do we got here? So it says what location will a cop meet and the motorcycle meet? Okay. So I have t now. I can use it for either one because they're going to be in the same spot. So I'll just pick one. Let's pick where will the cop be at 750. Okay, so it's going to be looking for xt equals xi, which was originally 0. And then he's traveling at 67, but he's moving down the line for 750 seconds. And this is going to give me my location at that 750. So grab a calculator, you punch that in here pretty simply. 67 times 750, and I got 50,250 meters. All right, so you can double check my math. 50,250, and the unit I'm using for distance is meters. If you do the same thing for this guy, but you need to put the 3,000 in there. Essentially, he's 3,000 meters ahead. All right, so that's xi plus vit, and if you put in the the 63 is the velocity of that individual, and then put in the 750, and you should get the same value because they're in the same spot. Okay. There we go. So this one here is set up very similarly. A student is walking down the hall, a teacher is 15 meters behind, and if the teacher jogs at 5 meters per second, okay, how much time will it take to catch a student? Okay. I'm going to change this problem a little bit just because it's very similar to the last one. Okay. So let's change it up a little bit here. Students walking down the hall at, let's say, walking down the hall. Let's say he's walking towards the student, towards the teacher. Okay, walking toward the teacher. So toward the teacher. Okay, and then the teacher's 50 meters behind. If the teacher jogs at 5 meters a second. Okay, and there's no accelerations here. So I'm going to give the kid. Let's say that the teacher's walking. The student's walking toward this and accelerates at, let's say, 0.1 meters per second squared. Let's give this student a acceleration. So let's map this out here a little bit. So I have myself the teacher who's walking this way at 5 meters per second, and then down the hallway is 50 meters, and the kid is walking this way at 3 meters per second, but has an acceleration of 0.1 meters per second squared. So let's set the math up on this one so we can see how this works. Now there's a frame of reference question here we really want to be aware of because this kid's moving to the left, which is why we changed it a little bit. And I'm not going to solve this whole problem. I'll just show you how to solve it. A, B, and C, you can solve it out on your own. It's a math problem. So this guy here, xi plus vit plus 1/2 at squared. I'm just going to equals to xt, which equals xi plus vit plus 1/2 at squared. All right, so this guy here is 0. This here, he's traveling at 5t. This is 0, so I'm just going to put plus 0 here. You can leave it out. Equals xt, which we're going to leave. Just leave it at that, I guess. We're going to take that out momentarily. And then this guy is 50 meters down the run. And then this guy is traveling at a negative 3t. And then has a 1/2 negative. Okay, so remember, a negative velocity and negative acceleration means that he's getting faster. Okay, so if he was traveling to the left, this would be another interesting problem. If he's traveling to the left, but he's slowing down at 0.1 meters per second. Okay, which that means he's got a negative velocity but a positive acceleration. That would be another interesting question. So every second he slows down 0.1 meters per second. But either way, so there now we're going negative and negative. Okay, so be aware of that, negative, and it's just 0.1, so not a ton. And then t squared. So how do we solve this problem? Well, because we have a square component and we have a non-square component variable factor, then we have to just do quadratic. So move everything to one side. So I'm just going to move, because it's got this 5t, I'm just going to move this over. So I'm going to minus 5t over here, minus 5t, and I get, in this case, I'm solving for this, and I'm going to have, okay, so I have 50 minus 8t, all right, and then minus 1/2 0.1 t squared. So this component here is 0.05. That would be that value here. Equals, and then nothing's left here, so it's just 0. So I'm not going to go through how to use the quadratic solver, but you should be using a quadratic solver on your calculator. And so in this situation, if you don't have one, you can find it. But we have the A, B, and C components here. So we have the three components are my A, B, and C. I'm going to grab my calculator here. All right, so the square component is A, and this is 0.05. This is my B component, and this is my C component. Okay, so in this situation, I'm not going to solve it all out. I could probably do that. A is going to be negative 0.05. B is going to be negative 8. And A is 50. Now my calculator gave me two numbers here. T equals, you should try it on your own, a negative 350 and a positive 190. So 190, so see, that's what my calculator gave me. I guess I should check to make sure it's right, but seems like a bit high. Moving at 5 meters per second seems a bit high. We could solve in here and see if it works. But let me try it one more time with the other program. One of my programs doesn't work all that great as far as quad solver goes. So we have A is negative 0.05, B is negative 8, and A is 50. All right, I see you're much better. Okay, that seemed a bit high. And I got negative 166, and I got 6. This one's not a real number. The answer is 6 seconds. And there we go. Wonderful. I'm glad I redid that. Okay. All right, so that's the gist of how a overtake problem and you could do lots of things this way. It could be something where, let's say, you throw a ball up in the air and it comes back down. And then while you're throwing that ball up, you throw a second ball up, a second or two later. Where does it meet? Okay, that'd be a nice problem as well. So I think what we got next here. All right, so let's stop there for now, and thank you very much.